All right. So we're going to cover dynamics now. I literally just covered everything on the AP test that you need to know and covered all of their formatting and everything there. And when I say literally, I mean I just stopped the recording and then hit the button again and then we got right back into it. You don't need to know all that, but that's fine. So let's talk about dynamics. So with dynamics, what we're talking about is things that make things change, which is forces, right? We're really talking about forces overall, and the idea is that they do cause an object to experience a change, right? If you are not moving and you start to move, then you must have experienced some sort of force. If you speed up or slow down, you also must have experienced some force. And a good way of recognizing that is knowing that we have these related concepts of force and motion, right? Changes in motion require forces. And in fact, that's a great place to start, is that Newton's first law literally tells us that, right? So actually, let's start covering those three things, because Newton's laws are the basis here for dynamics, right? So let's go Newton's laws, and I'm going to list all three of them. Okay. So I'm going to do that thing where I fast forward through all that, and you don't see me writing all that. Okay. So the Newton's laws are the basis here for this chapter. I know that's so stupid. I apologize. I have to have this light on so that you can see me, but it shoots directly into my stupid whiteboard, so let me move that. Okay. Nope, not going to change anything. And that's not even pointing at me anymore. Can you see me if I turn the light off? I don't think so, though. Well, that's not too bad. That's the difference between my computer camera and this camera. You don't care about all that. But there you go. Newton's laws. So there we go. That is the basis for everything here in dynamics. So that very first thing, you see I said changes in motion require unbalanced forces. That's what Newton's first law tells us. It's not what it actually says. So just make sure we recognize that there is a difference there, right? What does Newton's first law actually say? It says objects in motion stay in motion in a straight line forever without speeding up or slowing down unless acted upon an unbalanced force. And objects that are not in motion stay non-moving unless they are acted on by an outside unbalanced force, right? And it does have to be unbalanced, right? Because if it's balanced, then I don't experience that acceleration. Cool. So that's our first law. Again, Newton's first law states changes in motion require forces. If I have a change in my motion, if I turn direction, if I slow down, if I speed up, any of those changes, if I start moving when I wasn't, if I stop when I was moving, all of those things require unbalanced forces. Because if we have balanced forces, then those things cancel out and I don't experience any change. Cool. So Newton's second law is pretty much how we solve all the problems in this chapter. Newton's second law tells me that an acceleration is directly proportional to the force applied to it and inversely related to the mass applied to it. Another way of just saying that is the equation that I wrote here, which is acceleration is the total forces on the object divided by mass. So again, if an object experiences any sort of acceleration, it's because of the unbalanced force on it. That doesn't mean the totality of that unbalanced force, but the actual sum of that unbalanced force. And what we mean by that is, let's say that I have something that's pushing to the right here, and it's pushing to the right with 15 newtons of force. Remember that newtons are the unit of force. And something is pushing this direction with 5 newtons of force. Well, the unbalanced force is 15 newtons. But 15 newtons is not what causes my acceleration. It's the sum of those forces, right, which would be the 10 newtons difference. Right? So just make sure we recognize that, again, accelerations are based on net forces. So if I do see an acceleration, I can usually solve for what my net force is. So if they were to tell me an object is accelerating at 5 meters per second squared and it has a certain mass, well, then I can figure out what is the unbalanced or the net force on it. Now that net force doesn't tell me any individual force, which I will do some more examples here, but that net force does tell me what is the unbalanced force. And often I'm going to be able to have a list of forces and then a totality of my forces. And since they are representative of the same thing, then I get to set them equal to each other. And we'll do some examples of that here in a minute. And I can go solve for whatever piece I don't have. So let's say again, in the last scenario, I had what the two forces on the object were, but not the total sum of their forces. So I could use those two pieces to solve for the other one. But a lot of times we'll be given the acceleration and the mass, we'll have the totality of those forces, but not what each one of the individuals is. And that's what a lot of our math in this segment is. Right? So don't forget with this Newton's second law, that means that all of our acceleration formula from kinematics are also still in effect, right? If they gave me a speed and they told me the time I reached that speed over, then I would be able to solve for my acceleration and then go back to that formula. So don't forget that. Also, like braking distance, if they gave me the distance and like what my final speed was and all that kind of stuff, I could go back and solve for my acceleration and then come back over to this formula. Cool. Now, when we have this, net force is equal to ma, which is another way of looking at that, right? There's two ways of looking at that formula. My net force is equal to this ma. We know that any of the forces that are in that list can be generic, right? We have my net force. This is the overall force, right? That's kind of like a generic term for everything that's added up, if that makes sense. And then with each of my individual forces, there's going to be specific names of something that is applied to the object. So, for instance, let's say I take this marker and it's in my hand. Well, we know that the overall force on this object is 0 because it's not going up and down. That's a kind of a general term for it, right? The overall net force on this is 0, right? But what are the actual forces that are being applied to it? Well, again, in general terms, I have an up force and I have a down force. But very specifically, I have the up force of my hand being balanced by the down force of gravity. Well, or either way, whichever way you would prefer that, right? That the down force of gravity is being canceled out by my force up. But the idea being that, like, I can list these things out just directionally if I want to, just use these general terms and be like, oh, well, these are some forces that are on it. Or I can go through and say, well, each one of these terms has a specific definition or a specific title, and I can list those out as well. Now you might be saying, well, why are you mentioning all of that? Well, because remember, that means that we can have other formula that tell us what that particular force might be, right? There may be a certain point where like, oh, well, the force of friction, as you know, is u times the normal force. Well, that specific force is now going to be one of the forces that's in my list, and I can pump in a formula to help me solve for that stuff. And again, we'll do it kind of an idea here in a second. So, Newton's third law says that we have this force of one object on the other, force of object A on B, is equal to, but opposite of, the force of B on A. And that's that idea that every force has an equal and opposite force. That's what that means, right? What that means is that if I touch something, it touches me back with the same amount of force. Now, individually as items, me and the item I touch don't have to have the same forces on us overall, right? So I hold this marker up. Well, the marker has me and gravity on it, but I touch the marker, it touches me equally hard back. But I have a lot more forces on me than the marker does, right? I'm sitting in a chair, it's touching me, my feet are touching the floor, I'm touching this thing here. So there's a lot more forces that are on me that are not being experienced by the marker, right? And so in this case, yes, I touch the marker as hard as it touches me. That force has what we call an interaction pair. There is a partner that is the exact same. But that doesn't mean that the items individually experience those things in the same manner. So just make sure we remember that, right? Yeah, cool. So this subject is actually pretty straightforward, if I'm being honest. We're going to run through some ideas we need to make sure we remember, and some examples on how do we diagram things and that kind of that nature. But this idea overall is pretty simply covered here. Now we can still do forces in 2 dimensions, and that requires us to go back and do things like we did in kinematics with our sine and our cosine. But it still falls into the same general relative idea. I would do force x is equal to mass times acceleration x, and then all of a sudden it's the same basic idea, right? So let's cover, in terms of solving things, what is kind of like the most important idea here. So let's give an example here, and let's say that I have the following idea. It's a little wavy thing because I'm going to skip it till right now. So I'm going to diagram this thing a couple different ways just to kind of talk about the ideas in this chapter in terms of forces. So let's start with a ball rolling at a constant speed on a frictionless environment. And then we're going to add some stuff as we go along and kind of figure out, hey, what's going on here? How does that change things? And I think that overall idea will be enough to help you. Yeah, I actually don't think this video will have to be that long. Dynamics was, in my opinion, the easiest segment that we did. I know you guys probably liked energy better, which we'll get to, but dynamics is really easy in the sense that we are pretty much just diagnosing those ideas, right? We're really just, every single time we're doing dynamics, asking ourselves to look at an object. What forces are on that object? What direction are those forces? And then what's the overall effect of all of those things, right? And so I'm going to do that with this ball. We'll do that a couple different times, and we'll go from there. So, taking a look at this ball, again, we said that it's going at a constant speed, and it's doing so on a frictionless environment. So we're going to go through and we're going to say, what's going on with this ball? What are the forces that are on this ball? The first thing we're going to do is draw a free body diagram. With a free body diagram, we're going to place a dot that will represent the center of mass of whatever our object of interest is. Now, the object of interest in this case is a thing we call the system, and anything that acts on the system is a thing we call the agent. Now, every time I made you always list those things out. If you have a question that's on the test, just describe them. Just say, oh, in this case, the system is this, and the agents are this. These things are putting contact forces, these things are putting field forces. Why? Well, we want to be as descriptive as possible. We don't want to leave anything out. So we don't want to just go, oh, here's my diagram. You remember, the idea with the AP test and free response questions in general is it's not, oh, did you technically get the right answer? It's how much of a correct answer can you give. So just make sure you're doing that. Cool. So what we're going to do is we place a little dot, and we say, well, what forces are happening to this object? Cool. We place that little dot. Little red dot I'm using. So when we take a look at this ball and it's going on a frictionless environment, we ask ourselves, well, what forces are on the object? We can see that it's touching the floor. And because it's touching the floor and it's not accelerating up or down, those forces must cancel out. Well, nothing else is touching it, right? We know that it's touching the floor because of something else, right? Which is in this case gravity, which we're going to talk about. So we know that it's touching the floor because of gravity. So in this case, those two forces do cancel each other out. They are not the interaction pair we are describing. Ball touches floor, floor touches ball. That is your interaction pair. That is the things that are equal, right? So again, floor touches ball, ball touches floor. That's one interaction pair. Ball puts a force of gravity on the earth, earth puts a force of gravity on the ball. That's our other interaction pair. But do you notice that those interaction pairs are just another way of saying we have two forces on this object, each one of them must have a pair. Let's draw that out, okay? So we have this force down and a force up. And we have a force up. Cool. And I made my arrows roughly the same size. In this case, I'm trying to indicate that they are the same thing, right? They are roughly the same. They cancel each other out. I'm not accelerating up or down. Now again, those are general terms. So what are my force and my force up? Force down and force up. Well, we know that my force down is the force of gravity, and we know that my force up has a specific name, right? Well, what is the specific name for my force up? Well, if I touch something and I get this returned force of contact, we call that the normal force, or Fn, right? So now we have these two things. We have the force of gravity up and the force of gravity down and the normal force up. I have the normal force anytime I contact anything, right? That's literally what it means. It's this idea of I touch, you can't see this, I touch the marker, it touches me back, right? I touch my hand, it touches me back. I touch the screen here, it touches me back, right? All of those things are what we call the normal force. So from one perspective, there's always a normal force with any sort of contact, right? So in other words, like if I were to reach out and touch the camera, from my perspective, the camera's putting a normal force on me, but from the camera's perspective, it's touching me, and then there's this return force of contact, right? It's all about context. But that's all the normal force really means. Remember that normal means perpendicular to. The word normal literally means at 90 degrees to. So in this case, this force is perpendicular to the force of contact, which is the ground. So that line is going to be 90 degrees to the ground. Cool. All right. So again, we're just diagramming exactly what's happening. Ball is the system. The ground and earth are agents, right? They are enacting forces on this object. So that allows us to do the following. It allows us to say, what is the total sum of my forces? Well, the total sum of my forces is MA. The total sum of my forces is also Fn minus Fg. Cool, right? So we know that the total sum of my forces is always mass times acceleration. That's Newton's second law. The total sum of my forces in this case, let's actually sum those forces. Anything that's up is positive, that's the normal force. Anything that's down is negative, that's our Fg. Well, do not forget the following thing. In this case, my normal force is the force of gravity. So they cancel each other out. Don't forget that that means that my F net is 0. F net is 0. And also, do not forget we have this formula for the force of gravity. My force of gravity is mass times g, and g being 9.8. Cool. Now, the force of gravity, what does it represent? It represents how is your mass interacting with the gravitational field of a given object. that gravitational field is the same based on location or elevation. And so everything at the surface level of the Earth has the same gravitational field, which is, we are using 9.8 meters per second squared, or 9.8 newtons per meter if you prefer. Yeah, I think that's what it is. I think it's, you have to look that up. I apologize. Don't worry about that. That's not the point. But 9.8 meters per second squared. It's newtons per kilogram. Yeah, it's newtons per kilogram. That's not the point. That's really not the point. But the idea is that like we all experience that the same, right? 9.8 is for all things at that same elevation is the same. And so what we're really trying to say is, if I am more massive, then gravity has more of an effect on me, and if I'm less massive, gravity has less of an effect on me. And when we say less of an effect, I don't mean in terms of acceleration, we just mean in terms of the actual force, right? So gravity puts the same acceleration on all of us, but because we have different masses, we therefore have different forces. Remember that newtons measures forces, our weight is a force, our mass is a quantity that describes our inertia, our resistance to that change in motion. Mass is how much of us there is, right? Weight is how is acceleration affecting that to a certain extent, right? Again, it's a force. It's saying if I were to push this mass at this rate, what would it experience in terms of the forces? And if you're more massive and you accelerate at a different rate, well, then it makes sense that it would take more force to get you to do that, right? It's harder to push heavier objects. Okay, so let's take this exact same scenario and let's change a couple things about it, right? So let's take this exact same scenario and let's change a couple things about it, and I'll do that little like fast forward thing. So you may be able to see this. I now added green marker. Now why did I add green marker? Because this object is now going to be rolling on grass. Now what would we expect to happen if I had this ball which was on a previously frictionless environment and rolled on grass? Well, it's going to slow down. The grass is going to be putting this other force on there. So let's diagram these other forces and talk about what the difference would be, because we know that there should be now some difference, and there will be. So we go ahead and we diagram these forces, and I'm going to move my dot that I'm using to represent my center of mass away from the object in the interest of saving space. You should try to locate it close to it, but it'll be fine. So we still have a couple of my forces here. The normal force is still there, right? Actually, let me just go ahead. Yeah, the normal force is still there. The force of gravity is still there. However, I do have this new force, right? I do have this new force, and that new force is called the force of friction. Now notice that it is in the opposite direction that I'm traveling. There's nothing continuing to push this object, so there is one unbalanced force in the opposite direction that I'm traveling. Now, if force and acceleration, if force and motion are in the opposite directions, then you will slow down. If an unbalanced force and your motion are in the same direction, you will speed up. So we expect this ball to slowly stop as you go along. And you would obviously see that, or you would expect it. So we now have this new selection of our forces. So we know that our forces y cancel, right? So we know that our forces y cancel. Boom, sigma Fy equals 0. Now, let's point that out. Let's just make sure everybody knows that. We have this sigma F, and that's just the same thing as saying F net. Just as a heads up, remember, we have this sigma F, and that's the same thing as saying F net. It's just a shorter way of doing that if you want to do that. That sigma notation means the sum of, net means the sum of, they mean the same thing. But we know that my forces y cancel, so we don't have to worry about them. They're 0. That's easy to see. I don't accelerate it up and down at all. Don't even have to worry about them. However, I do now have an unbalanced x force, right? Which means that my sigma Fx is this force of friction. Bam! The force of friction. Cool. Sorry for the sound effects. I'm going to keep doing them because it's subconscious. Yeah, so I do have this force of friction. And since it's the only unbalanced force, it will be the only thing causing my acceleration. Since it's in the opposite direction of my motion, the acceleration will be negative, which will indicate that I am slowing down. Now, the acceleration will be negative provided that I made the velocity positive. The main thing is that their signs don't match. One's in the positive direction, one's in the negative direction. As long as that's true, then you will be slowing down. Cool. So again, make sure we recognize that. Now, we just talked about friction. We have not yet defined friction. Well, I mean, I guess technically I did in an earlier problem here, but the force of friction has this formula. So the force of friction is this thing called mu, which is this thing called the coefficient of friction times the normal force. So friction is based on two things, right? That's it. Those two factors. Literally just those two factors. How hard are you touching each other? That's the normal force, right? If I take my hands together and I try to move them back and forth, it's relatively easy. But if I squeeze them, it becomes harder. That's because of the normal force, right? And the other thing is this coefficient of friction, this mu. Now, what does coefficient of friction or mu mean? The coefficient of friction or mu represents very specifically this relationship between two materials, right? So let's say that I have sandpaper and I have wood. Well, their mu would be very high. That means that they're going to be very abrasive related to each other. And would say that I have two pieces of ice. Well, their mu would be very low because related to each other, there's not a lot of abrasiveness, roughness, contact points there, right? And so remember what we're talking about with friction is that idea, okay? And let's do one more thing. Or I'm going to do this, I guess, I got two more things I want to do with this ball, okay? Exact same scenario. Bam, we have this ball. I'm sorry for saying bam every time. We have this ball, but now it's being pulled by a rope. And now that it's being pulled by a rope, it is traveling at a constant velocity. Now, force from a rope is a thing we're going to call force of tension. The ball is still not moving up and down, so we don't really care about its up and down forces. We only really care about its side-to-side forces. Now, because I know that it is moving at a constant velocity, I know that it is got to have canceling forces. Now, I don't have any velocity up and down. I don't have acceleration or velocity, so I don't concern about those forces in terms of diagramming it here really at all. They're not affecting my motion. I'm not moving, and I don't need to know why I'm moving at a constant speed. Now, left to right, I have some forces, and I am moving, so I do want to try to figure out, well, what forces cancel out here? What provides me this area where I'm not speeding up or slowing down? Now, when all of my forces cancel, we call that a special thing, which is equilibrium. I enter equilibrium at that point when all the forces on me don't cause any acceleration. Now, that could be true if I'm sitting still, nothing's making me move, but if I'm moving at a constant speed, I also have no unbalanced forces on me. So going through and looking at this, we're only going to look at the x forces, and we look at the x forces, we'll see now we have this force on a rope, which is called force of tension, and we use Ft. And then we have this force the other way, which we're going to call the force of friction. Cool. So we diagram that and we say that. And that allows us to say that the sum of our forces x are going to be 0, because we know that I'm not accelerating. I know that I'm not accelerating, right? That's the same thing as basically saying it doesn't matter what their mass of this ball is, because this acceleration is mass times 0. Right. So I don't have to worry about it. But that does, and then I have this other thing that just tells me that the force of x is going to be this force of tension minus this force of friction. Cool. And so because I have this sum of forces, because I have this sum of forces is equal to 0, and this sum of forces is equal to all of these forces, I can set those things equal to each other. I can go 0 is equal to force of tension minus the force of friction. Right? Because the sum of forces is both 0 and those two things. And that allows me to add friction to the other side, and what I'll get is that the friction must be equal to the force of tension. Right? And again, that tells us what's going on with the ball. Why is the ball traveling at a constant speed despite the fact that it does have forces placed on it? Okay. And one last thing with the ball. One last scenario with the ball. And I can't think of anything else that we're going to need to do here. And this video has gone on a while, but that's fine. Ball's on a ramp. So, nothing else is interacting with the ball, and let's in fact say that this ball is frictionless, right? Or is on a friction environment. Excuse me. We said that there is friction on this ramp, but let's say that the ball still continues to speed up. So when we diagram this, it's going to give us a few interesting notes. So we're going to diagram this. So now we have something that kind of looks like this. So the ball has contact with the ramp, so it's going to have this normal force that comes off 90 degrees to the ramp. However, the ball's not going to accelerate up or down based on that surface of the ramp, so we know there must be a force canceling it, right? Which we're going to call this FGY. Now gravity acts straight down on the ball, but the ball is rolling down the ramp. And the ball is not accelerating up and down the ramp, which means that there must be elements of this FG, this force of gravity, which are in fact causing this motion to the left and right, and that causes this thing to stick on top of the ramp. So we have this FG, and it gets split in these two directions, to FGY and FGX. So now we're going to think about these things in this X direction, which we're going to call this here. We're going to call, oh, I'm sorry, I can't, it's hard for me to do this from the other side. We're going to call this direction here my X direction, and this direction is my Y direction. And I know that's weird, but that's fine. And so what we see is the forces in that direction, in this direction, right? Oh my gosh. In this direction, right? Oh my gosh. It's hard for me to do looking over it that way and doing it in reverse. I apologize. So the forces in this direction represent what we're going to call my Y forces, right? In this direction, they're my Y forces, and they cancel out. That's awesome, because we don't have to worry about it. There's no acceleration in that direction. And then my forces in this direction, they don't cancel, but I do have an overriding force downward, and that's where I would see that acceleration. Cool? Cool, 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 cool. And then again, in order for us to solve for those parts, what we would do is look at our triangle and make sure that our triangle makes sense when it comes to sine, cosine, and tangent. Find which side is our angle, and then go, okay, what's my opposite side? What's my adjacent side? And then just do SOHCAHTOA with that. Okay. Honestly, I think that's everything that you'll need for this particular piece for dynamics. I can't think of anything off the top of my head, anything else that I think will come up with that is going to be dire that you may have forgotten. So that's dynamics, again, just off the top of my head. I'm going through it. If there's anything else, you just let me know and send me an email and we'll go over it. So we still have circular motion and we still have momentum and work and energy that I'll cover in these videos pretty briefly. And I'll do that over here over the next 2-3 days and give you time to watch that going into our test next Thursday.